session number 3 of coordination compounds, we are going to practice the nomenclature of coordination compounds. In the previous session, independently we studied the naming of coordination compounds as cationic complex, anionic complex and neutral complex. Here I collect some random examples and will try to name these coordination compounds. The first and foremost very important step is identification whether the particular coordination compound contains cationic complex or anionic complex or it is a neutral complex. So we'll see the first example. So the first example, what I have written, K2ZnOH 4 times. We'll name these coordination compounds. Remember that sometimes they mention coordination pair with counter ions. Whole together is a neutral molecule if you have the counter ions as well as coordination pair. Sometimes they give only coordination pair with suitable charge, and in that case counter ion are going to not mention, and in such examples we need to write at the last ion. Now we'll see whether this particular coordination compound contains anionic complex or cationic complex or it is a neutral. We'll see now. So how to identify that one? So we have potassium, and potassium 1 plus it is, and totally 2 we have, therefore 2 plus I am going to consider. So if a counter ion is 2 plus, then definitely the charge of coordination pair is 2 minus. So this particular example contains coordination pair or complex ion with the negative charge. So negatively charged complex ion it is. So you need to know if it is anionic complex, then how you are supposed to name that. We used to write the first the cation name, and later we write the ligand name, and next we write metal Latin name, and oxidation state has to be written in a bracket with the Roman number. So that is how we write the naming of coordination compounds of this particular example. So how I am going to name that? So see here, the first one we have potassium, therefore let me write that potassium, and in this coordination pair the zinc what we have, that is central metal atom, and we have OH minus. OH minus is a ligand, isn't it? So how we write that? OH minus is a ligand and the name is hydroxo, and sometimes you can call it as hydroxido also, hydroxido. So hydroxo or hydroxido, you can consider anyone. How many ligands we have? How many OH minus ligands we have? 4 ligands we have. So we need to use the prefix, that is nothing but tetra. So potassium tetra hydroxo, or you can write hydroxido. Then we have a metal atom zinc, and I write here zincate. So see here, zincate we write here. Since it is anionic complex, the central metal atom should end with ate, zincate. And now we need to write the oxidation number in a bracket. So what is the oxidation number of zinc central metal atom? The charge of the complex is 2 minus. The charge of OH is minus 1, totally 4 we have, 4 minus I write. And now what about the charge of zinc? So that if you add with this 4 minus, we are going to get a 2 minus. Therefore one can say this should be 2 plus, because 2 minus 4 we are going to get a minus 2. Therefore the oxidation number of zinc will be 2. So this is the method how to calculate the oxidation number. And if you are not good with the direct calculation of oxidation number, you can go with the step by step as I said. So in the previous session I talked about that. Let me explain that once again. If we are interested in the calculation of oxidation number of zinc in the actual manner without using this kind of method, we have a potassium, it is 1, we have 2, and we are interested in a zinc, therefore I write it as X, and OH it is actually minus 4, therefore I write what actually minus 4, which is equals to 0, because all together the complex compound, that is a neutral. So if you simplify it for X, so we will be getting 4 minus 2 and we will be getting X is equals to 2. So you can do calculation of oxidation number of central metal atom in this fashion, or if you are quite good in calculation of oxidation number, directly writing the oxidation number above the respective species, you can calculate the oxidation number. It is left with you. You can follow this method or you can follow direct method, but you need to get the correct oxidation number. And if there is a slight change in the oxidation number and complete a different name we are going to get, and you are going to lose the respective marks for that one. So here the potassium tetrahydroxo and zincate hydroxo it is, okay, hydroxo. I have not written that hydroxo, so let me write that tetrahydroxo zincate and Roman number 2. And remember, if you write tetrahydroxidozincate, that is also right. As I told you that one, usually we used to write O, and O is going to be replaced by IDO, chloro, chlorido. Similarly, hydroxo, you can consider anyone. If you write hydroxide also, that is right. So since it is anion complex, we are supposed to write in this fashion. So remember, all alphabets are small alphabets only. There is no any gap between the coordination sphere, only a gap you should leave in between the counter ion and the coordination sphere. That is the first example what I consider. Next example we'll see CrEn 3 times and Cl3 we have. First we'll identify whether it is cationic or anionic or a neutral complex here. So what I do, so we have a Cl, the charge will be 1 minus, totally we have 3, therefore charge of this will be 3 minus. So if a counter ion charge is 3 minus, definitely the charge of the coordination sphere should be 3 plus. So 3 plus we got here, and we are supposed to name this, okay, and you can calculate the oxidation number directly here also. So En, that we know, ethane 1,2-diamine, that is a neutral complex, therefore the charge will be 0 and the charge of Cr will be 3 plus itself. So we'll name this one. The coordination sphere has a positive charge, cationic complexities. So in cationic complex, how we name? We write ligand name first, next central metal atom name, and in the bracket oxidation state of central metal atom, and last we write anion. So this is the fashion how we used to write that. So we'll see in this particular example, Cr, chromium will be the central metal ion, and we have En, that is a ligand. I hope you remember what is that En stands for. So En stands for ethane 1,2-diamine. Ethane 1,2-diamine. Actually how we write that is NH2, CH2, CH2, NH2. This is ethane 1,2-diamine. On nitrogen we have 2 lone pair of electrons that are going to be donated, therefore bidentate ligand. And remember, En is a neutral ligand because we don't have any charge on this species, so it is a neutral ligand. So we need to write ethane 1,2-diamine, but we have 3 En, so 3 times of ethane 1,2-diamine, and here we are supposed to use the prefix. So usually the normal prefixes like a di, tri, tetra we are supposed to use. As I said, in the ligand name itself, if you have a prefix, then you have to use the prefixes like bis and tris and tetrakis has to be used. So if it is 2, we are supposed to use bis. If we have 3 ligands, we are supposed to use tris. If we have 4 ligands, we are supposed to use the prefix as a tetrakis. In the name of ethane 1,2-diamine, in the name itself we have a prefix di, therefore I am not supposed to use di, tri, tetra, I am going to use bis, tris, tetrakis, since we have 3 En, therefore how I am supposed to write tris. And in the bracket we need to write the name. What is the name of the ligand? Ethane 1,2-diamine. Ethane 1,2-diamine. So ligand is over now. Next we have Cr, that is ethane 1,2-diamine, chromium. So this is cationic complex. Word should not end with ate, as it is we need to write chromium, and in bracket we write the oxidation number. What is the oxidation number? Oxidation number of chromium is +3, and anion is a Cl3, that will be writing as name as the ion. So anion, how we used to write, the same fashion we need to write. What is that? Chloride. So this together is a coordination sphere and this is a counter ion, so I have left space in between that. That is the IUPAC name of second example, tris ethane 1,2-diamine. chromium 3 chloride. So first one was anionic complex, second one is cationic complex. We'll see the third example. So third example, K3Al C2O4 thrice we have. So potassium plus 1, totally it is 3 plus, then the complex charge will be 3 minus, anionic complex, isn't it? So anionic complex, and a rule you need to know, and respective name we are supposed to write. So we'll calculate the oxidation number of this aluminium. So in this coordination sphere, aluminium will be the central metal atom, C2O4 will be the ligand. So do you know what is that C2O4? So let me write here C2O4 2 minus, and this we call it as oxalate ion. So this is the oxalate, and the symbol we have OX, which belongs to bidentate ligand, oxalate ion C2O4. So how many oxalate ion we have? 3 oxalate ion we have, and you need to write a trioxalate and aluminate. So since it is a anionic complex, cation has to be written first. Therefore let me write here. So this is potassium, right? Potassium, counter ion is over, leave a space, and trioxalato, and we have aluminium. Therefore I need to write a trioxalato aluminate. See here, aluminate it is, because anion complex word should end with ane, aluminate. And we'll see what would be the oxidation number of aluminium. Total charge will be 3 minus, this C2O4, what is that? Oxalato ion. So this will be 2 minus, the charge is 2 minus. So here I will write a 2 minus. If this is 2 minus, and we need 3 minus as the answer, so 3 minus as the charge, so what would be the oxidation number? So 2 minus is for 1 oxalato, isn't it? And but we have totally 3, therefore 2 minus into 3, and therefore I can write here this should be what actually 6 minus. And here 6 minus is the charge of oxalato, and this should be 3 plus. So 3 minus 6 we will be getting what actually 3 minus. Therefore the oxidation state would be what actually this is the 3. So oxidation state of this aluminium is 3. So the name will be potassium trioxalato aluminate 3 we have, and C2O4 2 minus is oxalate ion, OX, oxalato we call it as, oxalato, sorry, this is oxalato, not oxalato. So OX is a symbolic representation. This is how we write the name of the third example. Fourth one we will see K3Cr C2O4 3 minus. K3 we have, the charge will be 3 plus, the charge of coordination sphere will be 3 minus, isn't it? And now we'll calculate the oxidation number of Cr. So we have C2O4. C2O4 charge will be 2 minus. Totally we have 3. Therefore 6 minus R, right? So what would be the oxidation number of Cr? So that if you add with the 6 minus, you will be getting 3 minus, and this will be 3 plus, I can say. So we write the name of that one. So the name of this particular compound will be potassium, since it is anionic complex, potassium, and trioxalato, and we have a Cr, chromium, and chromate, and oxidation number is 3. In a bracket I will mention oxidation number 3, that too in a bracket in a Roman number. That is the IUPAC nomenclature of this coordination compound. We'll move with the fifth example. In the fifth example I have Cr, NH3 3 times, H2O 3 times, and Cl3. We'll identify what kind of a complex it is. So this is of the complex, so let me mention here, this will be 3 minus, okay, because Cl will be minus 1, so 3 minus it is. So this square bracket should be here. I think I mentioned the wrong example, so this square bracket should be here, because in the coordination sphere you should have central metal atom with the ligands. So 3 minus, then the charge of the coordination sphere will be 3 plus. So we have Cr as a central metal atom, and NH3 is a ligand, and H2 is a ligand. We'll see how to name this compound, and we came to know that since the complex has a positively charged cationic complex, and the ligand's name has to be written first, but it is the heteroleptic complex, because more than one different types of ligands we have. One is NH3 and one more is the H2O. As we know, NH3, the name of this ligand will be amine, isn't it? and H2O, the name of this ligand will be aqua, and both are neutral ligands because we don't have any charge over there. And if you have more than one different ligand, you need to write the ligand's name in alphabetical order. So we have AA same, the first alphabet is same, then move with the next one. The next alphabet is M we have here, and we have Q, so M comes first, therefore amine has to be written first. So we don't have one amine, we have three amine, so therefore I am going to write a triamine. Right. Next, one more ligand aqua. We have three aqua. Therefore, triamine, triaqua, triamine, triaqua. Then we have a Cr. So triamine, triaqua, chromium. Chromium. We'll see what would be the oxidation number of Cr. NH3 is a neutral ligand, H2 is a neutral ligand, and the charge itself will be the oxidation number of Cr3 plus, chromium 3, the charge will be 3, and we have anion, that will be Cl. Therefore this I write it as what actually chloride. So this is how this particular name I have written. So here the first example, this was anionic complex, cationic complex, anionic, anionic, cationic. So if it is anionic, the rule is different. If it is cationic, rule is different. First you identify what kind of complex ion it is and then follow the rule. So these are the 5 examples what I discussed. 5 more examples. 6 to 10 examples I listed. We'll name these coordination compounds. Example number 6. CO, cobalt, NH2, CS2, CH2, NH2 3 times. We have a coordination sphere with twice, and SO4 thrice we have. We'll see what kind of complex it is. SO4, sulfate 2, the charge will be 2 minus. But we have a totally 3, therefore the total charge will be 6 minus, isn't it? Whereas if the counter ion charge is 6 minus, means this coordination sphere charge is 6 plus. So cationic species it is. So in cationic species we write the ligand name first. So just you observe, they have mentioned NH2, CS2, CH2, NH2, that is as same as En. Instead of writing En, they have given the actual molecular formula of that bidentate ligand, ethane 1,2-diamine. So this ligand is nothing but ethane 1,2-diamine. So ethane 1,2-diamine, how many ligands we have? We have 3 ligands. As we know, ethane 1,2-diamine has already prefixed di, therefore bis, tris, tetrakis we are supposed to use with respect to ligands. Since we have 3 ethane diamine ligands, this for tris will be the prefix word what I am supposed to use. So let me write here. So the name will be tris. In the bracket I write ethane 1,2-diamine. Ethane 1,2-diamine. And where to write hyphen, where to write comma, you need to know. Ethane 1,2-diamine. And next we have a central metal atom. What is that? Cobalt we have. So let me write that cobalt. And we need to write the oxidation of state in the bracket, and the anion will be sulfate. So I leave a space and I write a sulfate here. Okay. So oxidation state we left here. So ethane 1,2-diamine will be the neutral ligand. Therefore the charge will be 0. Ethane 1,2-diamine. Then what would be the charge of cobalt here? The total charge will be 6 plus and cobalt, and but remember this coordination sphere is twice. Means in this coordination sphere, in this complex we have 2 cobalt and 3 into 6 ethane 1,2-diamine. Since the charge of cobalt will be 6, but here since we have 2, so 6 divided by 2 you will be getting the 3 plus. So 3 plus will be the oxidation state. So here in bracket I write the oxidation number state. What is that? Roman number 3. If you didn't get that, follow the actual method or very simple rule how to calculate the oxidation number. So cobalt we have 2. We are interested in cobalt. Therefore I write 2x. And ethane 1,2-diamine is a neutral. Okay. Totally we have 6. 6 into 0, 0. Then plus what we have? SO4. SO4 the oxidation state will be 2 minus, and totally 3 we have, therefore minus 6 which is equals to 0. Then 2x is equals to 6 and x is equals to 3 plus, therefore the 3 plus will be the oxidation number. So if you didn't get directly, you can solve somewhere and you can write the direct oxidation number. Try to know tris ethane 1,2-diamine cobalt 3 sulfate, since it is a cationic complex. We'll see 7th example. Cobalt we have, and we have a Cl2, En2, and we have a square bracket with plus. Now if you carefully observe this and now try to identify what kind of coordination complex it is. It is not a complete coordination compound because counter ions has not given. We don't have any counter ions. So we don't have any counter ions means there will be no balancing of the charge. Therefore we have a coordination sphere. We have a complex with a positive charge. So this is cationic complex. Only the thing is counter ions has not mentioned cationic complex. So in case of cationic complex, we write the ligands name first. So we have two different kinds of ligands. Heteroleptic complex, we have Cl, chlorido. So we have Cl, that will be chlorido, Cl minus it is, and we have ethane 1,2-diamine. So that we know that is En, and that will be ethane 1,2-diamine. Ethane 1,2-diamine. Ethane 1,2-diamine. So out of these two, I am going to prefer this chlorido, because when you consider according to alphabetical order, chlorido comes first. So how many chlorido we have? 2 we have. Therefore the name will be dichlorido, right? And we have ethane 1,2-diamine, and in ethane 1,2-diamine, since we have 2, you should not use di, and instead of that we have to use bis for that one, since it has already the prefix bis. And ethane 1,2-diamine, bis ethane 1,2-diamine. Since this bis is related to complete the name, therefore bracket you are supposed to use dichlorido, bis ethane 1,2-diamine. We have a cobalt. We have cobalt, and oxidation state we have to write in brackets. So oxidation state we will write that one. Total charge will be +1. Ethane 1,2-diamine is 0. This is a neutral ligand. Cl, the charge will be 1 minus. Totally it would be 2 minus. Okay. And now what would be the charge of CO? So that if you add with the 2 minus, you will be getting what actually plus. Therefore the charge will be what actually 3 plus. So here I am supposed to write the oxidation state will be 3. And if you didn't get that, just see. So cobalt we are interested in X, and we have Cl2, so that will be -2, and ethane 1,2-diamine will be 0, and which is equals to the charge will be +1. As we know, in case of ion, the sum of oxidation number is equals to the charge present on the ion. This is not a neutral complex, therefore 1 I have written. Therefore x is equals to 1 plus 2, you will be getting 3, therefore 3 I have written here. So this is the basic of oxidation number, how to calculate that. Example number 8, we have a cobalt, we have Cl2, En twice we have, and Cl we have. We'll identify what kind of complex it is. Cl we have 1 minus, therefore this should be 1 plus. So if you consider this particular example and just you see the previous example, example 7, both are almost the same, but the 7th example is ion, whereas 8th example is complete coordination compound, because in 8th example we have a counter ion, whereas in the previous example we don't have that one. So remember that if in the 7th example we have ion, we don't have a counter ion, therefore the word should end with the ion. So remember that after writing cobalt 3, it is compulsory to write ion. So this is the reason I consider the two examples in one side, to know this is ion, this is a coordination compound. So we have ion, means we don't have any counter ions, therefore the word should end with ion, whether that may be positive ion, negative ion, whatever it may be, the word should end with the ion. So we'll see this particular example which belongs to cationic. So we have two different ligands, chlorido and ethane 1,2-diamine. According to alphabetical order, chlorido we are supposed to write, so dichlorido, En we have, bis we are supposed to use, bis ethane 1,2-diamine, right? And then we have cobalt. Oxidation number, this will be neutral, this will be 2 minus, and ultimately this should be 3 plus. So cobalt 3. Now this is a coordination complex. We have ion as Cl, therefore chloride we are supposed to write here. So now try to know the difference between ion and a complete coordination compound, how to name that. Example number 9. Ti we have titanium, and H2O 6 times with square bracket T plus, and now this is not complete coordination compound because we don't have a counter ions, means the after writing the name we have to end with the ion because we have a charge over here. And now since it is a cationic complex, follow the rules of the cationic complex. First ligands we are supposed to write. So this is a homoleptic ligands because single kind of ligand we have, that is H2O. The H2O is neutral ligand, and what is the name we write? Aqua we write. So how many aqua we have? 6 aqua we have. Therefore I am supposed to write here what actually hexa aqua. Right? Hexa aqua. Ligand is over. Next we have Ti. That is nothing but titanium. And we need to write the oxidation number in bracket. So the total charge will be 3 plus. H2O is a neutral ligand, then ultimately the charge of Ti would be 3 plus. So oxidation number will be 3, and that is the name, complete name. Now since it is a ion, and therefore the word I am supposed to end with ion. So hexa aqua titanium 3 ion it is. And instead of ion, if you have somewhat like a Br, and you should end with bromide, Cl, chloride, SO4, sulfate, in that fashion. We don't have any counter ion, therefore I should end with the word as ion. Next example, example number 10. Pt we have NH3 3 times, H2O we have, Cl2 we have. So this is heteroleptic complex. We'll see whether it is cationic or anionic. So this is cationic or anionic, we need to identify, but we have only the coordination pair, isn't it? So we have a coordination pair, we don't have a counter ions. So now I compare with the previous example. So here we have only coordination pair without any counter ions. This example is also we have only coordination pair without any counter ions, but this will be cationic complex, this will be neutral complex. So why it is neutral complex? So in both cases we have coordination pair, but in the previous example we have a coordination pair with the charge 3 plus, therefore cationic complex. In this particular example we don't have any counter ions, we have only coordination pair, but we don't have any charge, therefore this belongs to neutral complex. Try to understand, cationic is different, anionic is different, and neutral is different, and that depends on the charge present on the counter ion. Okay, but here we don't have, charge present on the coordination pair. So here we don't have a counter ions, so we have a coordination pair without any charge, therefore this belongs to neutral complex. So neutral complex, how we name that? As it is, so we write the ligands first, and later we write the central metal atom name and with respect to oxidation number. So ligands, we have 3 different kinds of ligands. Amine we have, aqua we have, and chlorido we have. So let me write here. So first NH3 stands for amine. So we have amine and NH3. And next we have H2O. H2O we write aqua. Both are neutral. And Cl, that is nothing but chlorido, isn't it? And Cl minus. So among these 3, NH3, H2O, Cl minus will be the negative charge. So anion is chlorido, whereas NH3H2O both are neutral. And now out of these two, which one comes first? Alphabetical order we have to consider. So A we have and C we have. So C comes last. So first you need to consider these two. Since both are A, next alphabet you consider. So we have M, we have A. Therefore amine will be the first. After that we get aqua. After that we get chlorido. Identify based on alphabetical order. A, C we have, therefore C comes last and A comes first. So there is a competition between in these two. Next alphabet you consider, M we have, Q we have, therefore amine comes first. So how many amines we have? We have 3, therefore triamine. Right, triamine. Next we get aqua. So triamine, only one we have. Therefore triamine and aqua. So Cl2 dichlorido. Dichlorido. Pt we have platinum. And we need to write what actually the oxidation state in the bracket. So together is a neutral molecule, means the charge will be the 0, and we'll see Cl will be 2 minus, this is 0, this is 0. If this is 2 minus, to balance that this should be 2 plus. Therefore here the oxidation number is 2 actually. That would be the name of 10th example, triamine aqua dichlorido platinum 2. So in the name if you compare, as I said, this is cationic complex, this is a neutral complex. Cationic complex we have without counter ion, therefore we ended word with ion. But this is a neutral complex, therefore just as it is the name we need to write. So try to identify which one is cationic complex, which one is anionic complex, which one is a neutral complex. And if we don't have counter ions, then the word should end with the ion. Even though in the last example we don't have counter ion, but we don't have charge also. Therefore in this case you should not end with the word ion. These are the remaining 5 examples, totally 10 examples we discussed. 5 more examples, 11 to 15. 11th example you see, HgCO SCN 4 times. What kind of complex it is? Hg 1 plus coordination pair 1 minus anionic complex it is. So anionic complex, the name of the cation is going to be first name. So therefore the mercury. Next we have SCN minus. So SCN is ambidentate ligand. Ligand which contains more than one ligating atom or donor atom, but when complex is formed, one donating atom is going to be attached with the metal. And SCN minus is an example for that. In the previous session I discussed some examples of that particular ambidentate ligand. So observe here in this CN minus, so carbon is also ligating atom, nitrogen is also ligating atom, but at a time out of these two one is going to be ligated with that. So if you consider CN minus, carbon is going to ligate. If you consider NC minus, nitrogen is going to be considered ligating. And you can consider NO2 minus and you can consider ONO minus also. In this particular species, nitrogen is ligating atom, oxygen is ligating atom. Similarly, this particular example, SC minus what we have, sometimes sulfur will be the ligating atom, and in this particular example, nitrogen will be the ligating atom. In that case, the name will be different. This will be cyanido and isocyanide. Nitrito. This is thiocyanide and this will be isothiocyanide. So the names will be completely different. This is the one fashion how we write. One more fashion of writing we have. We need to write the ligating atom at the end of the ligand. For example, in this case of NO2 minus, if nitrogen is a ligating atom, we would have written the nitro-N or nitrito-N. Both are considered. Whereas in this case, ONO minus, nitro-O, you can write a nitrito-O. Similarly, in case of SCN minus, thiocyanate yes, we can write. And in case of NCN minus, thiocyanate N we can write. This is how we can write the name of the ligating atom after the name of the ligand. So mercury and SCN minus, we have 4 ligands. Therefore mercury tetra thiocyanate. Sulfur will be the ligating atom. Therefore I write sulfur because they have written in the fashion of SCN minus, means the sulfur will be the ligating atom. So sulfur, thiocyanate yes, and cobalt we have, since it is anionic complex, therefore cobaltate, and we need to write the oxidation number. So SCN minus 1 minus, totally it is 4 minus, this should be 3 plus, so that totally you are going to get 1 minus, therefore the oxidation number of cobalt will be 3. So cobaltate 3 you need to write. Next example, if you observe PTNCS 6 times 4 minus we don't have counter ions, means after the name we need to write ion. and here this is anionic complex. So anionic complex ligands has to be written first. So we have NCN minus 6 times we have, therefore hexa thiocyaneto. Here I write N because in the previous example sulfur was ligating atom with the central metal atom. Now nitrogen is going to ligate with that one. Therefore thiocyaneto N I write here. Okay. Next hyphen. Next we have PT and the name will be platinate. Platinate. And we write the oxidation number. So 4 minus we have, and this actually NCS 6 times. So this would be 6 minus. We have 1 minus for 1 NCS. Totally we have 6. Therefore 6 minus. So what would be the charge of platinum? So that if you add with 6 minus, you will be getting 4 minus. So the charge would be 2 plus. 2 minus 6 minus 4 we are going to get. So therefore the platinum oxidation number will be 2, and this is a ion. Therefore I write what actually ion after the name. Next example. PT NH3 2 Cl NH2 CH2 and Cl we have. So this is complete coordination compound. We'll see whether it is cationic complex or anionic complex. We have anion 1 minus, therefore this should be 1 plus. So cationic complex it is. So in the cationic complex we write the name of the ligands first. So we have 3 different kinds of ligands. Heteroleptic ligand, one is amine, one is chlorido. Do you know the name of NH2CH2? Methyl amine it is. So let me write that what are the different ions we have. So we have NH2, I am going to write here amine, NH2, NH3 which is a neutral ligand. We have a chlorido Cl minus. We have a NH2CH2. The name of the ligand is methyl amine, NH2 and CH2, methyl amine. So we have to write the name of the ligand. Since we have more than one, therefore we need to follow the alphabetical order. First A comes, next C and next M. Therefore amine has to be written first. So how many amines we have? 2 we have. Therefore the name will be diamine. Yes, amine is over. The next ligand will be chlorido. How many chlorido we have? Only 1. Therefore I write chlorido. Next we have methyl amine. So let me write that methyl amine. Only 1 we have, methyl amine in a bracket to differentiate that since we have here. And next we have a PT, that is the platinum. So now let me write here, that will be platinum. And we need to write the oxidation number here. Methyl amine is a neutral ligand. We don't have any charge over here. NH3 is also neutral. Cl will be 1 minus. Okay. And what would be the oxidative state of PT? So that if you add with the 1 minus, you will be getting 1 plus. So this should be 2 plus, isn't it? 2 minus 1, you will be getting 1 actually. So therefore the platinum 2, and we have anion. What is that? Chloride. So I am going to write here, that would be chloride. So this would be the name of the compound, diamine chlorido methylamine platinum 2 chloride. Example number 14. CuNH3 4 times SO4. SO4 would be 2 minus, therefore this should be 2 plus. And NH3 is a neutral ligand, 0, copper will be 2 plus oxidation number. Very simple to calculate the oxidation number of central metal atom. Cationic complex, ligand name has to be written first. So NH3 4 times, so therefore this would be tetraamine, isn't it? Tetraamine. And here we have CO, tetraamine, copper, oxidation number is 2, tetraamine, copper 2, sulfate. Copper to sulfate. So that would be the name of example number 14. 15th one, you just observe Ag we have, and we have a Cn twice, and the charge is 1 minus. Okay, and this is ion actually, so ion has to be written at the last, remember, and this is anionic complex. Anionic complex. In anionic complex we write the name of the ligand first. So we have a Cn, okay, and we have a 2Cn, therefore dicyanide. We have Ag. Ag is silver, As we know, in case of anionic complex, we write the Latin name. Okay, so Latin name I am supposed to write here. And what would be the Latin name of Ag? And some examples as I discussed, you need to know if it is iron. As I said in the previous session, usually the first alphabet will be the symbol of an element. Sometimes first two alphabets will be the symbol of an element. In some examples we have, and we consider the Latin origin as the name, and we consider these alphabets for writing the names. Fe, iron. But iron, it is English, but in Latin this is ferrum, right? And if you consider Pb, lead, but in Latin it is plumbum, right? And if you consider Cu, copper, but in Latin it is cuprum. If you consider some other examples like Au stands for gold, but in Latin it is aurum. Ag, if you consider, it is silver, and in Latin it is argentum. It is argentum. And based on the oxidation state, we write ferrous, ferric, plumbus, plumbic, cuprous, cupric, aurus, auric, argentus, argentic. We can write like this. So these are the Latin names, you remember. So how to identify that? If the name is completely in English and the symbol is not at all related to the alphabets of that, and that would be definitely the Latin words you are supposed to use. So therefore, dicyanide, and you should not write silverate. Anionic, the word should end with ate. You should not write silverate, you should write argentate, because Ag, argentum we have. Therefore, dicyanide, argentate. Okay, and what would be the charge? So this will be 0, and Cn is a neutral ligand, and therefore this should be what actually 1 we are going to get. So argentate 1 ion we are going to get, argentate 1 ion. That is the name of this particular compound, since it is a ion. Therefore dicyanide argentate 1 ion we are going to get, whether this ion may be positive or negative ion. That these are the examples. So totally 15 examples I consider just for practicing the naming of coordination compounds. Remember, take care of calculating oxidation number. First identify whether it is cationic, anionic, neutral. Sometimes they won't give counter ions, and in that case the word should end with ion in that fashion. But we have the ambidentate ligand. You can write the names here. Actually this particular example, so these two if you consider, here I have written thiocyanate S, and here I have written thiocyanate N. If you write only thiocyanate for that, that is also right. Whereas in this case, if you write thiocyanate, because nitrogen they have, if you write isothiocyanate, that is also right. And if you have NO2 minus ONO minus, if you write nitro, and if you write nitrito, that is also right. And you can write it as nitrito N, nitrito O. Ligating atom can be written, but according to latest IUPAC nomenclature, it is better to write the ligating atoms. So in NCERT we have such examples where ligating atom has been mentioned, and you need to observe that. So what are the Latin? These are the frequently used Latin words. So try to know. Fe, ferrate we write, and plumbate we write, and cuprate we write, aurate we write, argentate we write. And if you have just English name as it is, zinc, and the symbol is Z, and only zincate we write, platinum, PT, platinate we write. Okay, so only in these cases you need to know the names for that one, because in the last example I consider Ag, and you should not write silverate, you should write what actually the argentate. So all these are the 15 examples just for your practice to know better about nomenclature of coordination compounds. Next level of nomenclature of coordination compounds. Observe the example what I have written here. PTNH3 4 times, PTCl4. Now we'll name this compound. Till now we studied many examples, and in some examples we have a coordination pair with counter ions, and some examples we have seen with only coordination pair, only one coordination pair with some particular the charge. Whereas if you observe this particular compound, we have two coordination pair, means two complexes we have, and such kind of coordination compounds which has two complexes, and these we call it as double complexes here. So nomenclature of double complexes we'll see now. So nomenclature is as same. Usually what we follow the rules for naming of in general coordination compounds, the same rule has to be followed. But the very important part is we need to find out the oxidation number of a central metal atom. That is the very important task in case of nomenclature of double complexes. Whereas if you consider this complex, platinum is a central metal atom and NH3 will be the ligand. Whereas if you consider the next complex, platinum is a central metal atom and Cl will be the ligand. So two central metal atoms we have. And these two central metal atoms sometimes have same oxidation number. In some examples it is different oxidation number. So we need to find out oxidation number of platinum in this particular complex and oxidation number of this particular complex, and we need to write the name. And one more thing is, practically the first complex what we write, that would be cationic complex. Usually the charge, if we calculate, the charge will be plus. And the second complex what we write, that would be minus charge anionic complex. This you just keep in your mind. In case of double complexes, the first complex will be cationic and the second complex will be anionic. While writing the name of this particular complex, follow the rules of cationic complex. While writing the name of this particular complex, follow the rules of anionic complex. And the very important is we need to find out the oxidation number of the metal. So first I will tell you incomplete how to name this particular compound. And initially oxidation number calculation is very important one. So here the actual method to calculate oxidation number of platinum, in both cases the method we follow, we call it as hit and trial method. So we don't guess any oxidation number in a particular manner because charge we are not aware of that. So randomly we consider a charge and will predict what would be the oxidation number of the central metal atom. So the method I call it as hit and trial method. So we'll see how actually hit and trial method will help us to know the charge of the oxidation number. So this will be the cationic, this will be the anionic as I said. So first I am going to consider the first complex, that will be PT NH3,4. This will be the cationic complex, and I consider here one more, that is PtCl4, that would be the anionic complex. So charge we don't know that one. Hit and trial method, randomly we consider the charge. So I will start with 1 because the charge would never be 0 because that would be the neutral actually in case of double complexes cationic and anionic. So initially I consider it as 1 plus and I consider it as 1 minus. Similarly next we will see 2 plus and 2 minus, next we will see 3 plus and 3 minus, 4 plus and 4 minus. We will calculate the oxidation number of platinum. So before that you should have knowledge of what would be the variable oxidation state of platinum. And we have discussed about the S block elements, P block elements, D and F block elements also, and we aware of the elements which has variable oxidation state and what are the variable oxidation states of the respective elements. Platinum belongs to D block elements. It has two different types of variable valency and they are 2 plus and 4 plus. So in a coordination complex, platinum coordination number will be 2 in some compounds and it is 4 in some compounds. So 2 and 4, and we'll see what would be the actual and in which case we are going to get the respective oxidation number. So hit and trial method 1 and 1 I consider. So we'll see that one. NH3 will be the neutral molecule and therefore the X plus 0 is equals to plus 1. Therefore X is equals to 1 plus we are going to get. That is oxidation number of PT. If we consider charge will be plus 1 and if I consider charge will be 1 minus, what will be the oxidation number of PT? So X minus 4, 1 Cl 1 minus, therefore 4, which is equals to minus 1, and X is equals to minus 1 plus 4 and X is equals to 3. So here we got oxidation number of platinum as plus 1 and plus 3 if we consider the charge as plus 1 and minus 1. We'll see what happens if we consider plus 2 and minus 2. So PT NH3 4 times, and this I consider it as 2 plus, and one more PtCl4, and the charge I consider it as 2 minus. Let me assume that. So X we have, it is a neutral ligand 0, and we have a 2, and X is equals to 2 plus, we are going to get that will be the oxidation number of platinum in this particular compound. We'll see if it is 2 minus, what will be the oxidation state. PtX we have -4, which is equals to 2 minus we have, and X is equals to 2 minus plus 4, and X is equals to 2 plus, or you can write plus 2. So here we got, this will be the oxidation number if we consider 2 plus and 2 minus. Let me move with the next one. So 3 plus and 3 minus if you consider. So PtNH3 4 times we have, and 3 plus I consider, and for this particular one more complex PtCl4, and I consider it as 3 minus. We'll calculate the oxidation number X, since it is a neutral, and 3, and X is equals to oxidation number 3, we get that one. 3 plus we will be getting the oxidation number. For this particular complex PtX, and we have a -4, which is equals to -3, and X is equals to -3 plus 4, and X we are going to get it as 1. So 3 and 1 we get. So similarly you can consider it for +4, -4, +5, -5, randomly hit and trial method I consider. But here if you consider +1 -1, we got +1 +3, 2 plus 2 plus, and 3 1. But practically from the knowledge of platinum, we know that platinum has a 2 variable valency, +2 and +4. But if you consider this one, we got +2 oxidation state when we consider the charge as 2 plus, the charge as 2 minus. Therefore, from this hit and trial method, I say that the oxidation state of platinum is 2, and in this compound oxidation state of platinum is 2. So this is how, by randomly considering 1, 2, 3, and by knowing the oxidation state of the platinum or respective central metal atom, we would guess by using hit and trial method what would be the name, what would be the oxidation state of the particular compound. So now what I am going to do, I will write the name. So now we came to know, so the oxidation state is 2 plus here, and oxidation state is 2 plus. Okay, so we'll write the name of that one. Cationic complex, in the same fashion we have to write. So we have amine. So the name I am going to write here, this will be tetraamine platinum. Tetraamine platinum 2, right? So cationic complex is over. Now I consider anionic complex. Anionic complex, here we don't have any the cation, directly we write here. So this is also 4Cl we have, therefore tetrachlorido, and we have a Pt, and that I write it as platinate, tetrachlorido, and platinate, and the oxidation state will be 2. So the name of this particular double complex is tetraamine platinum 2 tetrachlorido platinate 2. That is the name of nomenclature of this particular compound double complex. This is the way how you are supposed to write the name of that. But this method, the method what I told, hit and trial method, is time consuming. So to calculate the oxidation number of central metal atom, it takes time. In the competitive examination also it takes time. So this method I am not going to follow. We will see one alternative method to calculate the oxidation number of central metal atom. I have a shortcut method for you to identify the oxidation state of central metal ion in double complex. What is that? Instead of following trial and error method, you need to follow the 6 terms what I have written here. So what is this 6 terms stands for? If you know these 6 terms, and you can write oxidation number of any metal in double complexes easily without following hit and trial method. Observe here, what is that? If a coordination number is 6, what is coordination number? To the central metal ion, how many number of ligands has been attached is termed as a coordination number. The number of coordinate bond present in a complex, we call it as coordination number. So if coordination number is 6 And if we have 3D series ions from scandium to zinc, and the oxidation number would be definitely 3. If we have a coordination number 6, and then the elements are platinum and palladium, oxidation number would be definitely 4. If we have coordination number 6, and if that is 3D series ions from scandium to zinc, the oxidation number would be 2. If we have coordination number 4, platinum, palladium, silver, we have coordination number would be 2, and coordination number 2 we have zinc, cadmium, mercury, oxidation state should be 2 here. If coordination number is 2, gold and silver and copper, the oxidation number would be 1. So if you know this, and without following hit and trial method, we can write the oxidation number of that. It takes very less time to write the name of this. So we'll write the name of these remaining 4 examples what I considered. First one I explained here. Now we'll see the first example I explained by following the hit and trial method. Now we'll see whether you follow the shortcut method, whether we get the same oxidation number or not. So here platinum we have. So platinum, so 4 ligands we have, means 4 coordinate bond, means coordination number of this platinum will be 4. So coordination number is 4, isn't it? Coordination number is 4, and a platinum we have, and the oxidation number would be 2. Therefore 2 I have written. Yes. Similarly, in this particular complex, coordination number is 4, and platinum we have, coordination number is 4, platinum, and the oxidation number is 2, oxidation number is 2. Directly we got, isn't it? So similarly we'll see some other examples. So this will be the cation and this will be the anion. We'll write the name of that one. So diamine. Diamine. We have Ag, silver. We'll write the oxidation number. Next, the next complex. So here we have dicyanido, Ag we have, argentate, and we need to write the oxidation number. Don't get confused. We have Ag, we have Ag. In cation we write the name as it is, whereas in anion we write Latin name. Therefore silver I have written here, and argentate I have written. We'll write the oxidation number. So Ag is going to be surrounded by 2 ligands, means coordination number of Ag will be 2. So we have coordination number 2, and Ag we have 2, oxidation number is 1. So directly I write 1. That's it. Now in this compound, Ag we have coordination number is 2, coordination number is 2, Ag we have oxidation number is 1, oxidation number is 1. That's it, over. Next example. Cationic species and anionic species, we have 2 different ligands here. So what I am going to draw, here we have a chlorido and this is amine. So amines first comes, therefore tetraamine. Okay, tetraamine, dichlorido, cobalt. We write the oxidation number in bracket. Of course, we have square bracket with 3, and we are going to name it for only one complex. You try to know about that one. Similar examples we have solved. Next, I will come to the next example, next particular complex, CrCN6. So, hexa, cyanido, Cr we have, chromate, ATE, chromate, because it is anion complex, hexacyanido, chromate, and oxidation number we write. So we'll see. Cobalt is a center metal atom, and how many ligands we have? 2 plus 4. Totally 6 ligands we have, 6 coordinate bond we have. So 6 coordinate bond we have. If we have cobalt, 6 coordinate bond, here we have 6 coordinate bond. So cobalt belongs to 3D series, isn't it? So 3D series, therefore oxidation number would be 3. Therefore I write here 3. Cr we have, and coordination number will be 6. Coordination number 6. Chromium belongs to 3D series, therefore the oxidation number is 3. So oxidation number is 3. So try to know, if you know this shortcut method, we can write oxidation number directly. Next particular example, this will be cation and this will be anion. Follow the rules. We have 2 different ligands. Amine comes first, therefore this will be tetraamine, dichlorido, tetraamine, dichlorido, platinum, platinum. We write the oxidation number. And next species we consider PtCl4. So tetrachloridoplatinate. Tetrachloridoplatinate, and we write the respective oxidation number. So platinum 4 plus to 6 ligands we have. So coordination number 6 will be 6, and platinum we have oxidation number is 4. So I write oxidation number 4. And for this particular PT, coordination number is 4 we have. So platinum we have with 6 oxidation number, but here we have platinum with 4 oxidation number, 4 coordination number. So Cl4 we have. So platinum coordination number will be 4. In that case, oxidation number is 2. So oxidation number is 2. So try to know, in the previous 3 examples, for both will be of the same oxidation number we got. Sometimes oxidation number will not be the same. So here in this particular example 4 we have, and here we have 2. One more example, cationic species and anionic species. So 4 we have, 4 amine, therefore tetraamine, copper, oxidation number we write, and tetrachlorido, PT we have, anion, since anion, therefore platinate, tetrachloridoplatinate, oxidation number we write. Copper we have, and coordination number is 4. So coordination number is 4. Copper belongs to 3D series. Oxidation number would be 2. PtCl4, coordination number 4 we have. Platinum we have. Coordination number 4. Oxidation number is 2. So oxidation number is 2. So this is how we name the double complexes in this fashion. Remember that if you have a compound with 2 complexes, and that we call it as double complexes, and usually the first will be cationic, second will be anionic. The name would be as same as normally we write for the coordination compounds, but oxidation number has to be calculated by hit and trial method. That is the actual method to calculate that. Since it is time consuming, therefore I follow one shortcut method. So this is the method what you are going to get. So know this table what I have written, and if you know this one, you can write any kind of nomenclature of a double complex. So that will be complete of nomenclature of coordination compounds.